Hi again. Welcome back to this mini course on topological Four manifolds. Recall that the goal for these recorded lectures is to give you the outline of the proof of the following theorem, that if you have smooth, closed, simply connected oriented Four manifolds, they're homeomorphic if their intersection forms are isometric. And we already saw in the previous lecture how to prove this portion that's due to wall, that this gives us a H-cobordism between these manifolds. And today, in this video, I want to give you the proof due to Friedman of why H-cobordisms are topologically products in this setup. So here's the statement of Friedman's theorem. We have a 5-dimensional, smooth, compact-oriented, simply connected H-cobordism between four manifolds M0 and M1. These are also simply connected. In this situation, we know that this cobordism W is in fact homeomorphic to the product M0 cross interval. Moreover, we know that if I look at this homeomorphism a bit closer, if I focus in on the restriction on the lower boundary, that's in fact the identity map. And then if I focus in on the restriction to the top boundary, that will be a homeomorphism from M1 to M0. So this will complete the proof of the theorem from the previous slide. You should really compare this to the results of Smale that we proved in the previous set of lectures. One very notable difference between them is that here we only get a homeomorphism at the end. The outcome of Smale's theorem was a diffeomorphism there. So we'll see why we lose category like this in this theorem. Along that note, just like Smale's result, there's also a corollary here related to the Poincare conjecture. So if we use Wall's theorem from the previous slide, we see that every smooth homotopy for sphere is homeomorphic to Sn. So a slightly weaker form of the Poincare conjecture is a direct corollary of this result plus Wall. Okay, so let's get started with the proof of this theorem. The initial setup is now pretty familiar to us, so I'm going to essentially skate through this, just like we did in Smale's theorem, Smale's proof, and in Wall's proof. We start with this H-cobordism W, and by pretty standard moves, we can assume that it has only 2 handles and 3 handles. I'm going to assume for simplicity of this video that there's precisely 1 2-handle and 1 3-handle. The argument does not change very much. It just becomes more complicated to talk about all the pieces. So I invite you to think about what to do when there's, of course, some finite number of 2 handles and 3 handles instead. Of course, the number of 2 handles and 3 handles will be equal. So in this situation, let's assume we have a single 2-handle and a single 3-handle. This middle dimensional Four manifold, I'm going to call it M1 half, like last time. And we also saw that this middle level can be identified with both the connected sum of M0 with S2 cross S2 and the connected sum of M1 with S2 cross S2. There's a duality here that comes from turning that 3-handle upside down. It will be a recurring theme. So let's look at where that S2 cross S2 comes from. We kind of talked about this last time, but it was a bit fast, so let's do it again. So I want to think about this lower half of the H-cobordism. And so that's built out of this product M0 cross interval. And then there's a 5-dimensional 2-handle that gets attached onto there. And so here, this bottom boundary M0 is right here. And the top boundary is this part right here. Okay, that's by definition of what a handle attachment is. And now I want to sort of find for you these S2 cross S2s in this manifold. So if I look at this handle, I see that there's the belt sphere, which is showing up over here. And that's a copy of an S2. So that's going to be one of the factors of that S2 cross S2. And then the other factor is going to come from the attaching sphere somehow. The attaching sphere looks like this at the moment. That's the portion where the handle got attached to M0 cross I. But I would rather think about pushing that attaching region off to the edge a little bit. So I'm going to look at something that's over here. And then because I know that M0 is simply connected, I know that there's some embedded disk bounded by those light blue points in M0 cross 1. And so that's some nice embedded disk. And I'm going to cap that off with a push off of the core of the two handle. And together those two embedded disks give me the second S2 in my S2 cross S2 summand. So notice, of course, that this bottom portion that I drew in M0 cross 1, that's embedded. That was one of the exercises from last time. So here are the two S2 cross S2s in this connected sum with S2 cross S2. They're quite nice. They're embedded two spheres inside of this middle dimensional, this middle level of the H cobordism M1/2. They interact very nicely with each other. They intersect at precisely 1 point. In this picture, that's the intersection right here. Unsurprising, that's how the factors in S2 cross S2 should intersect with each other. And then similarly, by turning this decomposition upside down, we have a similar description of M1/2 as the connected sum of M1 with S2 cross S2. And these two factors will show up there as well. The thing is, these two factors interact very nicely with each other. These two factors interact very nicely with each other, but we don't necessarily know how these two descriptions interact with each other sort of across the way. But we do know something. We know that this is an H cobordism. So if we look at the handle chain complex for the relative homology, I only have 2 handles and 3 handles, so it's extremely simple. C3 is made out of it's generated by the 3 handles, in which case we have only 1. And similarly, C2 is generated by that 2 handle. And because I have an H cobordism, I know that there's no relative homology. So this map delta 3 has to be particularly simple. And so by the definition of delta 3, what I know is that if I let P be the belt sphere of the 2 handle, that was in blue in the previous picture, and then if I let Q be the attaching sphere of H3, what delta 3 tells me is that the algebraic intersection number of these two spheres in M1/2 should be 1. And so that means I have a picture that looks something like this. So here's my belt sphere coming up, and here's my attaching sphere in red. And the intersections between them, in this picture, I've drawn 3 of them. I'm going to assume there's 3 moving on just for simplicity. There's this extra pair of intersections that's canceling plus and minus. Okay, I have to choose some orientation just to get a basis for this handle chain complex. And then what I know from the discussion on the previous slide, I know that P has this partner, which I've drawn in light blue, which intersects P precisely once. And then Q has a partner that intersects Q precisely once, that I've drawn here in light red. But I don't know how light blue interacts. Like light blue could go off and intersect with red. I don't know that at the moment. And then light red could also interact with blue in some interesting way, and we don't know that. Anyway, that's some fact for later. But here, forgetting the light blue and light red for a second, I'm looking at my blue sphere P and this red sphere Q. These are both framed embedded spheres in this 4-manifold M1/2. And my goal, as ever, when I'm trying to prove something about an H cobordism, I want to cancel the corresponding 2 and 3 handles. And I have to think about, well, when can I cancel 2 handles and 3 handles? I can do that precisely when the attaching sphere of the higher guy intersects the belt sphere of the lower guy precisely once, geometrically. All I know right now is this algebraic information. So my goal is to isotope Q, that's isotoping the attaching region of the 3 handle, until the intersection between P and the new Q is a single point. And in that case, I would be able to cancel the handles. There'd be no more handles left in my H cobordism. It would be trivial H cobordism, which is all I've ever wanted. Okay. All right. So how will we do this? So in the bottom there, I have my picture P and Q from before. And it turns out, I'm going to kind of skip this, those light blue and light red curves that I had drawn in the previous slide, they don't quite do the thing that I want, but I can manipulate them geometrically up to an isotopy of Q, which is allowed, so that I can get for myself some new partner spheres, P perp and Q perp, that are quite nice, that play well with both P and Q. So what that means let's look at p perp for a second. So p perp intersects p at precisely 1 point, that one. And p perp does not intersect q at all, just leaves q alone. And then similarly, q perp intersects q at precisely 1 point, that one. And it leaves p alone, doesn't intersect it at all. And these are immersed. That's the price I had to pay, so they're no longer embedded, but that's okay. They have some double points, and they're also framed. So they have a trivial normal one, whatever that means. So in this situation, it turns out that I know that I can find for myself some framed immersed Whitney disk for this extra pair of intersections. So I have a Whitney circle that goes from plus to minus along red and then back along blue. And then I find for myself this framed immersed Whitney disk. I'm going to avoid talking about framing as always, immersed because M1/2 is, that is M1/2 by the way, is simply connected. And then it's an exercise for you to figure out that this complement is in fact simply connected as well. And that's going to come from the fact that we have these p perps and q perps. So enjoy figuring that out. It's a nice exercise. And so what I have at the moment is I have this immersed Whitney disk. It's framed in the complement. So in my list of 3 questions from the previous part, I've answered 2 of them. And now what I need to do is I have to embed this disk delta somehow. And if I could do that, then everything would work out very nicely. But like we saw last time, in general, I can't just replace any immersed disk by an embedding. I need to have some extra input. So I want to apply the disk embedding theorem, for which I need a partner for that green disk. I need to find an algebraically dual sphere for that green disk. So where will that come from? Unsurprisingly, that's going to come from our Clifford torus. So here's a picture of the Clifford torus again. So in this, that's a point of intersection of blue and red in the middle. And we saw in the previous part that there's this torus shown here in purple that goes around that point of intersection. So that's an S1's worth of S1s that's drawn over there. So I want to add in the Whitney disk to this picture. So the Whitney disk is pairing up 2 points of intersection, of which this is one. So the Whitney circle shows up like this. It has a portion along blue and a portion along red. And the green disk and the Whitney disk is somewhere like that. We see that it intersects the Clifford torus at a single point, that one. Okay, so that's quite nice. So I have that intersection. So I have the duality that I'm looking for, but of course I only have a torus at the moment. I really need a sphere. So I want to do contraction, which I did in the previous video, but for that I need some caps. So where are the caps going to come from? Well, the factors of the Clifford torus were meridians of the surfaces P and Q, so they bound meridional disks for P and Q. So what do these meridional disks look like? Here's one of them that's showing up entirely in a single time slice. And then the other meridional disk is sort of weirder to see, but it's showing up as the sequence of arcs like we saw last time. And then in each case, we see that the meridional disk intersects the red and blue surfaces precisely once, because that's what meridional disks do. So I don't quite like that. I want my capped surface to lie in the complement of P and Q, because that's where I want to apply my disk embedding theorem. So what I do is for each of those points of intersection, I tube into these P perps and Q perps that I had to help me. So you can see here was that point of intersection in the middle. I just take a connected sum of that disk with a little push off of that P perp. And so as a result, what I've now produced after this tubing is I've produced a capped surface in M1/2 minus P and Q. And then I didn't go over this very much, but in this picture, the tubing is a bit weirder to look at. But once again, I can take this connected sum of the meridional disk with a push off of, in this case, P perp instead. All right, so now my capped surface is in the four manifold that I want. I can do my contraction. And when I do contraction, I produce for myself an algebraically dual sphere for delta. And why is that algebraically dual? Well, I have this point of intersection, which does not get affected at all. And then I don't really know how delta and P perp and Q perp interact with one another, but because I did this symmetric contraction process, I know that these new intersections are not really going to count. And so the only intersection that gets picked up is precisely that one, which tells me that algebraically there's a single point of intersection between delta and its new partner coming from the Clifford torus. So this is very exciting. What I have now is, returning to my previous picture, I had this green immersed disk in the complement of P and Q, and this Clifford torus construction gave for me this algebraically dual sphere that I wanted. Again, it now lies in the complement of M1/2, in M1/2 in the complement of P and Q. And so now I can apply the disk embedding theorem to this disk delta inside of this manifold. We already saw that this thing is simply connected. That was your exercise. And so then when I apply the disk embedding theorem, my disk delta becomes improved to this disk delta bar. And in fact, the boundary remains the same even up to framing. So nothing exciting is happening over there, which is lovely, because what do I have now? I have a framed embedded Whitney disk delta bar for this extraneous pair of intersections between P and Q. So I can do the Whitney trick on Q along delta bar. This is an isotopy of Q, those are allowed. Once I do this, let's call the result Q bar. All these extra intersections of P and Q are now gone. All I have left is a single intersection of P and Q bar. It's a single point of intersection. So that means that the corresponding 3 handle and 2 handle can be canceled. So I cancel them. And so my H-cubordism doesn't have any handles, and therefore it's trivial. And that brings us to the end of the proof of Friedman's H-cubordism theorem. The key ingredient here, as you saw, was the disk embedding theorem. In the next video, I'll give a brief outline of the proof of the disk embedding theorem. Okay, see you there.